Hello, everyone. Welcome to Vancouver virtually. My name is Hama. I am an assistant professor here at Simon Fraser University. It is a great pleasure for me to tell you about our recent research progress on using intelligent planning techniques for large-scale multi-agent systems. So let's first look at our recent Blue Sky project jointly with NASA's Ames, where we are looking at deploying hundreds of autonomous aircraft towing vehicles in the near future at the Dallas-Fort Worth Airport. Here, after an airplane has landed on the runway, we need to assign the airplane to an autonomous vehicle to tow the airplane all the way from its runway to its assigned terminal gate, and vice versa from the gate to the runways for takeoff, so as to reduce the pollution produced by the airplane engine and energy consumption, human workload, traffic congestion on the airport surface, and eventually to reduce the size of the airport while still keeping the same throughput of the airport. Even humans can make bad decisions from time to time. How can the system make intelligent decisions for these teams of agents? I will talk about AI planning and search techniques that are inspired by the multi-agent coordination problems that arise in such large-scale multi-agent systems. But before that, let's look at one such multi-agent system that is already running today. That's the automated fulfillment centers by logistic companies such as Amazon and Alibaba. Imagine if you order a teddy bear online, the system will send a robot to move the shelf that contains the teddy bear all the way from its storage location to the packing station that needs the teddy bear. The human worker at the packing station will just pack the teddy bear with other products in the order and then ship them together. This so-called goods-to-person fulfillment model can significantly increase the throughput of the system while reducing the workload and safety hazard of the human workers, since the workers now only need to stay or even sit in the packing stations and wait for the goods to come. In this talk, I will tell you about how the planning and search techniques we've developed can be used to tackle some of the fundamental issues in the system where hundreds of robots need to be tasked to deliver shelves and navigate safely through the narrow corridors and busy traffic in the warehouse. In this direction, I would like to highlight one of our joint projects with Cainiao, a logistic company within Alibaba Group, where we develop planning techniques for an automated sortation center that has contributed to a new one-day sales record of over $30 billion during the Singles Day online shopping festival in 2018. That also dealt with the resulting over 1 billion express parcels that were then shipped throughout China within 1 week. Here, a human worker or a scanning machine will scan the delivery address of a parcel and put it onto a robot. The delivery address will be also input to the robot, telling the robot which sorting bin on the floor it should deliver the parcel to. Each sorting bin is associated with a certain postal code. It's required that in seconds of computation time, the system needs to make decisions for hundreds of robots about from which station the robots should obtain a parcel for delivery and on which route the robots should navigate to the sorting station and then to the sorting bin. I will also talk about how we use planning and search techniques to develop a software that recently won the NeuralRips 20 Flatland Challenge, a railway scheduling competition that was held in partnership with German and Swiss railway companies that have attracted more than 700 participants from over 50 countries. We won the competition using planning and search only that can scale to 3,000 trains and also outperform all reinforcement learning-based approaches. And we are also looking at tackling the multi-agent coordination problems that arise in many other real-world multi-robot systems, including automated grocery packing system, automated parking system, and automated port, which can, in our opinion, be tackled with AI planning and search techniques also. Given the current state of AI, how do we direct its research towards solving these applications of large-scale multi-agent systems? In viewing these applications as multi-agent planning problems, there's a key research question that cut across all of them, namely how to make fast and good decisions. Here, by fast decisions, I mean I'm referring to efficiency of the algorithms, namely fast computation time and large number of agents within a given computation time. And good decisions, I'm referring to performance measures such as effectiveness. That means high throughput of the system and low operating cost of the system. For example, few robots are needed for a given throughput if we have high effectiveness. And robustness, that means no collisions should happen between robots and no deadlocks should happen if we run the system for a long period of time. And first, let's look at path planning. When AI people look at the warehouses and the airports, they say that the problem is just to deconflict the agents while the agents are navigating. So we model this problem as multi-agent path finding, or MAPF in short. So throughout this talk, I will use MAPF. And the problem is just to find collision-free paths for multiple agents from their given start locations to their given goal locations. So we use a discrete model where each agent can either stay at its current vertex or moves to a neighboring vertex on a given graph at each discrete time step. We aim to minimize some objective function, for example, mixspan, which is the maximum of the arrival times of the agents at goal vertices, or flow time, which is the sum of the arrival time steps. And we need to avoid collisions. And vertex collisions where two agents attempt to occupy the same vertex at the same time step, and also edge collisions where two agents attempt to move along the same edge in opposite direction at the same time step. Why is this problem so interesting or exciting? Many logistic companies actually plan paths for single agents individually because we can solve single agent path finding problems well. And then they adjust the speed of the agents to avoid collisions during execution. While this works in most of the scenarios, it doesn't work in all cases. For example, here we have two agents. Agent 1 wants to get to here, and agent 2 needs to get to here. And what happens if we plan paths for them individually? They will follow their individually optimal paths. For example, here until agent 2 arrives at its goal vertex, and there's actually no way for agent 1 to get to its goal vertex. So that means in this scenario, agents have to coordinate, and we have to plan paths for the two agents jointly. So for example, what we want is that agent 2 move into the alpha way to let agent 1 pass. And both agents can arrive at their goal vertices safely without collisions. So when we look at this problem, the first question we ask is how hard is it to plan paths for multiple agents, and how hard is it to solve MAPF? There are existing NP hardness results showing that it is NP hard to optimize the mixspan and also optimize the flow time for MAPF. We've contributed a new result showing that MAPF is NP hard to approximate even within ND factor less than 4/3 for mixspan minimization. So MAPF is hard, but we still want to come up with algorithms that can provide very good solution quality. So in AI, we always solve NP hard problems, so the complexity itself doesn't scare us away. So I will give you one example. It's an approach developed from an Israeli research group, not from us, but back in 2012. It's called conflict-based search, or CBS in short, which is one of the state-of-the-art MAPF algorithms, and also complete and optimal for MAPF. So CBS is a two-level algorithm. It plans paths for single agents on the low level, and it performs a best first search on a binary tree on the high level to resolve collisions in the computed path returned by the low level systematically. And since it's a best first search, then CBS always expands the node with the smallest mixspan. And whenever CBS expands a node, it resolves a conflict collision and generate two child nodes that correspond to two options of resolving the conflicts. And then until it tries to expand a node without any collisions in its path, then it returns the optimal solution. We have also made several scientific contributions on this topic, namely to scale up the optimal MapPath algorithm based on CBS. So think about CBS, it's a best first search, just like Dijkstra algorithm or uniform coarse search. So that means we can add admissible heuristic guidance for its high-level search. So if we do so, we can scale CBS up, and we can speed up CBS by up to 50 times. And on top of that, if we do symmetric reasoning for the search, and then we break the symmetry, the key idea is to add multiple constraints at a time to its high-level search nodes, but still keeping its completeness and optimality guarantee. So if we do so, we can further speed up CBS. And the other way to speed up is that we look at solution spaces under the two subtrees of a node. If we want the spaces to be disjoint, then we can develop a better way of expanding the nodes. So that further speeds up CBS as well. As you can see in the result, we are talking about planning paths for 100 agents optimally in a few minutes. And also, in practice, we want even faster algorithm. So here we've contributed an anytime bounded suboptimal MapPath algorithm, which is also complete and keeps a suboptimality bound that is improving over time. And also we can stop at any time and then get a solution. Also, we've contributed new results on prioritized planning, namely just planning paths for agents according one at a time, according to a given priority order of the agents. So we proved that theoretically, this is not optimal even for any given order of the agents. But it is complete for well-formed instances where agents can sit in a parking location without blocking other agents, which is true for warehouses and railway scheduling scenarios. And also, we've contributed a new algorithm called Prioritized Based Search, or PBS in short, which combines the simple prioritized planning with a greedy depth-first search version of CBS that searches in the space of all possible ordering of agents, which also produces close to optimal solution quality empirically. So I'm talking about less than 5% suboptimality in reality. And on average, for 100 agents, it requires only 0.14 seconds of runtime. And for 600 agents, it requires only half a minute of runtime. We are also looking at different applications of MapPath. So here we are looking at agents that have shapes or volume. So we translate this into a new model where each agent can occupy more than one vertex. And we also generalize the vertex and edge collisions to, the way to do that is we pre-compute the collision set for each vertex and for each edge. And then we've contributed a new algorithm that is based on CBS by adding multiple constraints at a time, but still keeping the completeness and optimality guarantees of CBS. So an idea very similar to the symmetric breaking reasoning for CBS we've talked about earlier. The other application we have been looking at is multi-agent navigation tasks for robots and video game characters, where the agents trying to keep design formation. So here we are asked to balance between minimizing the mixed-band and the cost of deviating from the desired formation. And we've contributed a new approach that combines swarm-based approach from the robotics community, for example, the leader-follower approach, and also CBS. So as shown in the demo, the agents can keep the formation while they navigate through open spaces and also congested areas in the environment. So I want to highlight that MapPath itself is a fast-growing area of research, and we are also part of the MapPath research community together with researchers and groups from all over the world. In the past few years, we can also see many papers on MapPath published per year at each of the major AI conferences. And so far, we have organized several workshops, tutorials on major conferences, and published introductory papers that target general audience. We have also maintained a web page, mappath.info, that you can refer to for more information on MapPath. So given a MapPath plan, how can the agents execute the plan safely in the real world? Here we are looking at challenges such as robots are not completely synchronized during execution, and they do not move exactly at the nominal speed, and they have unmodeled kinematic constraints that are not considered during the planning. So during planning, we are actually using models that are not completely accurate. So we first look at one type of such system dynamics here, where agents can be delayed during execution. For example, agent 1 is moving along the path A, B, C, D, and then agent 2 is moving along the path B, C, F, C. So there might be an uncertain delay here when, say, agent 2 moves from C to F. So given such MapPath plan, we translate the plan into a total order on locations visited by the agents, where we can actually visualize this as a directed graph where each edge represents a precedent constraint. For example, a constraint that agent 2 has to visit location C before agent 1 visit location C. So the insight we get is that during execution, we need to keep the order in which two different agents arrive at the same location as specified by the MapPath plan. So for example, here, we need to make sure that agent 2 leaves location C before agent 1 actually enters location C. So we need to keep this order. And we develop a new algorithm called minimal communication policies for execution, which allows for decentralized, robust, namely collision-free plan execution of the agents. And also, it attempts to reduce the communication cost between the agents by calculating a transitive reduction for this directed graph. So the key idea is to reduce the number of edges between different agents that are not necessary. So with this knowledge in mind, we actually entered the NeuralRips 20 Flatland Challenge, which is also a MapPath problem with uncertain delays. And also it's a well-formed instances, namely chains are not on the graph before they depart from the stations and after they arrive in stations. We won the competition using planning and search only. The key idea is to use prioritized planning, which is very fast, and use large neighborhood search, which is a local search method to improve the MapPath plan. And once we have a plan, we can use minimal communication policies during execution to avoid collisions during execution, even under uncertainties. And then we allow partial replanning for agents that are affected by delays. One insight we get from the competition is that for the competition, it's more important to make fast decisions than making perfect decisions. We further extend the idea of dealing with delay uncertainty to handling other system dynamics that have not been considered in our past planning phase. So the key idea is to make use of a simple temporal network, or STN, to post-process a MapPath plan, which can be calculated very fast in polynomial time. This STN takes into account edge lengths and velocity limits, and also guarantees a safety distance among robots, and can avoid replanning in many cases. So the key idea is similar to the delay uncertainty to MCP, where we just construct a directed graph but also we associate time bounds to this directed graph. For example, the lower bound showing here, we can actually get it by the safety distance that we need to maintain divided by the velocity, the maximum velocity limit of the agents. And also with that knowledge in mind, we develop a plan generation and execution framework. The key idea is to first solve a hard problem. For example, run CBS to find a good MapPath plan. And then we construct an STM for the plan and then come up with the execution times for the agents. And the agents will just follow the execution times and until they deviate from the plan. So instead of replanning, we can actually go back to step 2, where we just need to solve a new STM, which is very fast in polynomial time, and then determine the speeds and then the times for the robots for execution. And only if we cannot solve the STM, meaning that the deviation is very large, very big, then we have to go back to first step, and we need to solve an NP-hard problem again. We actually demonstrate this framework using real robots, and here we have up to 5 iRobot Create 2, and then you can see that robots can execute the plan safely, even with some motion noises that are not modeled. Also, we've observed that in some scenario, planning path is not sufficient, and agents need to decide which destination they need to go. So, for example, we are looking at different teams of agents here in the warehouse, where we have first team on the agents that are moving to the storage locations. The task is to assign empty storage locations to the agents, also plan paths for them to get to the storage locations. Meanwhile, there are agents that are moving to each of the package stations, for example, package station 1. And it doesn't really matter which agents get to package station 1 first, as long as all the agents get to package station 1. And that means it doesn't really matter like in which order, the order in which they arrive at package station. So the placing into the incoming queue of package station 1 actually doesn't matter. So we model this idea as target assignment and pathfinding problem, or TAPF, where each team is given as many goal locations, called targets, as there are agents in the team. As long as one agent moves to one target given to its team, and each target is visited by one agent at the end of the same team, then we are happy. So the goal is to assign targets to and plan paths for the agents so that the overall mix span is minimized. Of course, agents cannot be assigned targets are given to other teams. So we contributed a new theoretical result showing that TAPF with more than one team of agents is NP-hard to approximate within any factor less than 4/3 for mixed-band minimization. And also we've contributed a new TAPF algorithm which combines CBS that to coordinate different teams of agents, and also use a mean cost maxwell algorithm for solving the problem for each team of agents. And this algorithm can compute an optimal solution for over 400 agents in 1 minute. And we also demonstrate this algorithm together with the post-processing step we have for MapPath post for a formation control problem for multi-robot system. So as you can see here, we have 2 teams of robots, and each team has 4 robots. And the robots can arrive at their goal locations without colliding with each other, even with a model motion noise and also dynamic constraints that are not considered in our model. And we are also looking at another challenge, namely agents need to be retasked after they arrive at the targets or at their goal vertices. That means agents need to be assigned new tasks after they finish their current ones in many applications of multi-agent systems. And agent needs to decide which task to execute next, and also they could not block each other from executing new tasks. So here we model this problem as multi-agent pickup and delivery, or MAPD in short, which you can view it as a lifelong generalization of the one-shot task and task planning problems, such as MapPath and TapPath, where a task might enter the system at any time, and agents have to constantly attend to a stream of new tasks. And we model each task to be a pickup location and a delivery location, and the agents needs to find a path to the pickup location first and then to the delivery location. And we've contributed 2 categories of algorithms, decoupled, where we assign a task to and plan a path for one agent at a time. And it has good scalability and can be extended to a fully distributed setting in reality. And centralized algorithms, where they assign tasks to and plan paths for multiple agents at a time. And it has good solution quality, but it's slower than the decoupled algorithm. So we guarantee that for all algorithms, all tasks, finitely many tasks can be executed in a finite time. And also for different algorithms, we can trade off between better solutions and faster runtime. So for the 2 categories of algorithms, decoupled has the potential for real-time computation, but not quite yet. So here we improve decouple by using a novel advanced data structure that allows efficient operations, for example, collision checking and inserting and deleting paths that is required in an online setting. And as a side benefit, it can also take into account kinematic constraints directly during planning compared to using a post-processing step, a post-processing approach such as MapPath post. As you can see here, all the robots can follow their path safely. Also, we further tested algorithm using 2,000 tasks and up to 250 agents. And as you can see, to compute a plan here, it requires only less than 10 seconds of runtime. So that's about 30 minutes of operating time of 200 agents for 30 minutes. So that's much much efficient and effective than using a discrete MapD algorithm plus using MapPath post for post-processing the computed plan. Also, in scenario where the information of the future tasks are known, we can optimize the order in which the agents execute the tasks. So we formalized this problem as a special version of TSP and come up with the TSP tool, traveling salesman tool with small mixed-map. And then we use our MapD algorithms to actually assign the tools to the agents and also plan paths for the agents. So this results in a family of improved centralized offline MapD algorithms where we utilize the task scheduling with the knowledge of future tasks and can produce solutions quality that are higher than online algorithms. And also, if we do the task assignment and path planning jointly, as we've done for TapPath, and we can make the algorithm even more efficient. So we apply this idea of our online MapD to the sortation center, which is also a version of MapD, but to optimize the idle time of stations. We tested our algorithm in an industrial simulator using real-world data. So as you can see here, we can scale to over 300 agents in 2 seconds of runtime. And then we improve the throughput of the existing system by up to 12%. And to summarize, we have contributed an algorithmic framework for coordinating long-term task and path planning operations to address a series of challenges arising in large-scale multi-agent systems. For our ongoing research, we are trying to develop a deeper theoretical understanding for long-term task and path planning. And we are looking to apply our algorithms to systems with high-order dynamics. With that, I would like to conclude the talk by thanking my collaborators, Sven Kornick, Nora Ayanyan, Daniel Hariber, and Peter Stuckey, and Ariel Fellner, Craig Tovey, and Alibaba's Cainiao AI team, and also many other MapPath researchers. And that's it. Thank you for listening to my talk.